Okay, this lesson is on inverses of functions. So for every function, there is an inverse of that function. And the inverses of functions become important, as you'll see when we get to some of the word problems. But the inverses of functions allow us to solve for certain variables when we don't have variables solved. It's well, you'll see when we get to some of the word problems. But today we're going to focus on just how to find the inverse of a function. So what you see here is a pair of functions that are inverses of each other. So, first of all, what do they look like? And so how can we recognize when something is an inverse or not? And then how to find those inverses. So what we're going to do first is we're going to graph these. And one thing you may want to do is graph these on your graphing calculator and look at them as well. But I'm going to graph them on the graph right here. So we're going to start off with the first function a, where it's f of x equals 4x plus 3. And g of x equals x minus 3 over 4. We're going to graph them on this graph right here, and then we're going to look at them and see exactly what they look like. So the first one is pretty easy. You could probably just graph it in your head, but what we're going to do is we're going to create tables of these. So, and let me just highlight this so we know what we're doing here. We're going to be doing those ones. So whenever we're substituting values in, we want to get a couple negative numbers and usually 0 and then a couple positive numbers. So usually we try to plug in like, -2, -1, 0, 1, and 2. And we're going to plug it in for x and see what we get. So -2, 4 times -2 is -8, plus 3 is -5. -1 times -4 is -4, plus 3 is -1. 0 times 4 is 0, plus 3 is 3. And 1 times 4 is 4, plus 3 is 7. And 2 times 4 plus 3 is 11. So we're going to graph these on this graph right here. If I can, there you go, zoom in. So I have -2 is -5. So down there, I have -1 and -1. I have 0 and 3. I have 1 and 7. And 2 and 11 sort of just goes off my graph a little bit, but I'll put the dot up there anyways. And so we have this line, and I'll try my best to draw this as straight as possible, but it's not quite the same as Notability. It doesn't draw a line for you. But that, in essence, is our line. So now, like I said, you could have probably just graphed that using your head, doing the y-intercept being 3 and the slope of 4, going up 4 over 1. You could have done that. But we're going to use the tables just so you can see something in a second here. So let's graph the next one. The next one is g of x, which is x minus 3 over 4. So again, I'm going to put in values for x. Now this one is a little bit tricky, so I'm going to give you the input values just so for the sake of, so we can see this. I'm going to give you input values to make sure that they fit on this graph. -5, -1, 3, 7, and 11. So when we put in -5 in for x, see, there you go. We get -5 minus 3 is -8 divided by 4 is -2. And -1 minus 3 is -4 over 4 is -1. 3 minus 3 is 0 over 4 is 0. 7 minus 3 is 4 over 4 is 1. And 11 minus 3 over 4 is 2. So, and then we're going to graph these over here. Let's see. Okay. I'll even change the color just so you can see this. So we have -5, -2, -1, -1, 3, 0, 7 and 1, and 11 again goes off the graph, but I can do that dot there. So I'm going to draw this straight as I can there. And so we're going to look at these graphs and just sort of, infer some information about these. So knowing that these graphs are inverses, and when we graph them, or know that these functions are inverses, when we graph them, we can see that there is some sort of similarity, okay? Some sort of relationship between these. So it turns out that when you have inverses of each other, they are reflections of each other from a diagonal line. So when one function is the inverse to another, its graphs will mirror each other across a line that is y equals x. So let me label these real quick before I forget. This was f of x, and this one is g of x. The line y equals x is a diagonal line that runs right through the middle of a graph. So what we can see, and maybe, let me see if I can maybe do a dashed line. And maybe highlight it. What we can see is how the black f of x and g of x are mirror images of each other across that diagonal. Another thing that we'll notice with inverses also is, did anybody catch, or did you guys catch, the similarities between the two functions? Does anybody notice that, the difference between these and these and these and these and these? Notice how the input column, and let me do that with a pointer here. Notice that the input column and the output column are reflected over here as well. So these functions are inverses. This doesn't work with any function. I can't just put in the same numbers and get the mirror image of those points. Again, this happens because these two functions are inverses of each other. We notice that our input values and output values are mirrored over here, so that now the output values are the input values, and they reflect. And so we can see that in several cases here. All these B, C, D, if you want to go ahead and graph B, C, and D into your graphing calculator, you can, and you'll see the same thing. You'll see two graphs that are mirror images of this sort of imaginary diagonal line that runs right through the middle here. Okay, so you can do that if you want to, but I wanted to show you how in one example here, if we put them into a table, both of them into a table, and actually graph them, we get a mirror image of them across this diagonal. And we can see with the points that are here that the inputs and outputs have been reflected. So if I didn't have these, I could, if I just had this, if I wanted to see whether or not this is an inverse, I would just put the outputs in the inputs of the other function and see if I get the mirror image or those inputs from the other function. So what we end up noticing, you can write it down here. What we end up noticing is that inputs and outputs have switched places. So how do we actually find the inverse of a function? How do we know? I mean, I told you that these two functions were inverses of each other, and so it's real easy to sort of make this connection. But how do you know what the inverse of a function is? Well, it all stems from this concept here. If the inputs and the outputs of one function are here, then the inverse of that function's outputs would become the input. Essentially, the x and y values have switched. Notice our input and output, or x and y over here, is now y and x over here. So if we use that concept that the x's and y's flip, when we go to the next page, here, we can switch the x's and y's. So inverse functions. Two functions are inverses if the domain, or x, of one function is the range of the other, or y, and vice versa. In other words, the functions will undo each other. The inverse of a function f is also a function if and only if it passes the horizontal line test, but we don't really need to worry about that. So remember what I said. We know that functions are inverses of each other if the x's and y's switch. So if I just have one function like this, okay, I can figure out its inverse by simply just changing the x's and y's around. So f of x, we know, is the same as just y. Okay, it's y equals 2x plus 3. So the first step is we're going to change the x's and y's. We're going to swap the x's and y's so that now y is x and x is y. Because remember, inverses of each other, their x's and y's have been switched. So now all we need to do is solve for y again, and that'll be our inverse. So this is the original function here. So now I'm going to solve for y. So subtract 3, subtract 3. And so I get x minus 3 equals 2y, and simply just divide by 2. So I'm going to flip this around. So y equals x minus 3 over 2. Or you could divide each one individually by 2, so you would have y equals 1/2 x minus 3/2. Though I don't know if many of you will do that. You'll probably just keep it like that. But either way. So what we know is by taking the original function, and just like in the graphs we saw, by flipping the x and the y, we can actually find its inverse. So this right here is the inverse of the original f of x equation. And a little bit later, you'll see how you can prove that. So let's try another one. Let's try another one that's a little bit more difficult. Like maybe one that's like a fraction or something like that. So again, here is the original function. F of x equals 2x plus 5 over 4. So we're going to change f of x so that it's just y equals 2x plus 5. You probably, most of you might skip this step, but I'm going to now switch the x and the y around, because that's how we find the inverse. Make the y an x and the x the y. And then I just solve for y, and I'll have my inverse. Well, we start this one by getting rid of the fraction, so multiplying by the denominator. Multiplying by the denominator, multiplying by the denominator. Okay. So 4x equals 2y plus 5. Okay. Subtract 5, subtract 5. So 4x minus 5 equals 2y, and then just simply divide everything by 2. So I'm going to flip this around again. So y equals 4x minus 5 over 2, and that will be our inverse. And you could graph them if you wanted to. You could graph the original, and you can graph the inverse and see how they are flipped. You could even check the inputs and outputs and see that they have been flipped as well. Again, but we'll show you a little bit later how can you prove that this is an inverse. Okay, you will have to, in some cases, find its inverse and then also prove that it is in fact an inverse. Okay. So we'll do, well, we can do all these, that's fine. It's the same thing here. So again, just dealing with a cube, so it might be a little bit different here, but same thing, we're going to change our function notation into normal notation, so y equals 2x to the third plus 1, and then we're going to switch our x's and y's and solve for y. First step, move 1, so I have x minus 1 equals 2y to the third. Okay, didn't mean to zoom out. Divide by 2, we've got to get the variable by itself. And so now I have x minus 1 over 2 equals y to the third. Now, we got rid of squares by square rooting. How would you think we get rid of cubes? It's cube rooting. So we can cube root both sides. Cube root both sides. That gets rid of the cube, and so my inverse of that function is the cube root of x minus 1 over 2. So same concept. And we'll do the last one here. So this one again, let's change colors here. We're going to change the function notation to normal notation, 2 radical x minus 3. Flip our x and y, x equals 2 radical y minus 3, and then just solve for y. So first thing I can do is, well, divide the 2 over. Remember when we're solving these, you have to get the radical by itself, so I'm going to isolate the radical. So now I have x over 2 equals radical y minus 3. At this point I can't do anything, so I have to get rid of the square root by squaring both sides. That'll get rid of the radical. So now I have x over 2 squared equals y minus 3. And then simply just add the 3 over. So I'm going to rewrite over here y equals x over 2 squared plus 3. Now technically, I mean, you do have to, distribute this in there, so it'd be x to the second, which is just x squared, 2 to the second, which is 4, and plus 3. And so that would serve as the inverse to the above function. So that's inverses. It should be somewhat easy. The math part might get some people, but the concept of inverses, just switching the x and y and then just solving for y, should be pretty okay. So the question is, now, how do we prove? How do we prove that that is in fact its inverse? And this is how you do it. So you will be asked on tests and quizzes to prove that in fact the two functions are inverses of each other. So if f and g are inverses, and this is why we did composite functions, f of g of x will give you just x, and then g of f of x will give you x as well. So putting g function in for f gives you x, and putting the f function into g also gives you x. So if you do both versions of the composite functions and get just x, then they are in fact inverses of each other. So this is why we did this last class. So we have f of x and g of x. The first thing we're going to do is do f of g of x. So what that means is that this is our input, which means that this right here is going to be inputted into the x in the other equation. So let's do that. So I have 3, and instead of x, I'm going to replace it with the g of x function, which is x plus 1 over 3 minus 1. Well, when I multiply this, because the denominator is 3 and I'm multiplying by 3, it actually just cancels out the denominator, leaving me with x plus 1 minus 1. Plus 1 and minus 1 cancel, leaving me with just x. Okay, well, that one worked out. That one's an x. Well, now we have to verify that by checking the other way around. So we're going to do g of f of x. So now the f of x will become the input into the g function. So let me erase this now so we don't get too confused here. So now this becomes the input for this. So let's see what that looks like. So instead of x, I now have 3, oops, that's how we changed to a pencil. 3x minus 1, and then plus 1 over 3. Well, again, the negative 1 and plus 1 cancel, and then you have 3x over 3, which so 3 and 3 cancel, leaving you with just x. And since both versions gave us x, they are, in fact, inverses of each other. That's it. Hope it helped.